Well, good morning, students. It is time for day two of our online class. I saw lots of comments from you yesterday. Um, some of them were some pretty good questions, some of them were some, let's say, interesting questions. Um, so here's where we're at. I want to just review again with you some guidelines, couple of maybe slight changes to some of this. We are going to use Google Classroom for our platform for communicating with each other. Your work will be posted in Google Classroom by 8 o'clock each day. Most of what you are going to do will also be turned back in through Google Classroom. If something else has to be done, I will let you know. And yesterday I said your daily work needed to be done by 10 o'clock. I'm just going to say, unless stated otherwise, your daily work should be submitted by 8 o'clock the following day so that when I come and I try to look for things, I can find it. So, what else? We're going to use the Google Classroom stream page to share basic questions. We don't, today's questions and comments were whatever you wanted to put in within reason. But as we move forward, let's try to limit that to legitimate questions about our content and our class work, please and thank you. And the virtual office hours 10:30 to 11:30 and 2 o'clock to 3 o'clock. That just means those are the times that I am going to be especially careful about trying to watch my computer for messages from you, whether it be email or in our Google Classroom. I'll tell you today, every 10 minutes or so, I went and scrolled through. Were there any new comments from your class? Were there any new comments from my other classes? And then I would do a couple other things, and I would come back and check again. So that's my plan for the time being. All right. So where are we at? Um, if I were to ask you about binary stars, star clusters, galaxies, I would want you to be able to give me some sort of definition or description. Within the star clusters, we talked about open clusters and globular clusters. Can you tell me some ways in which they are different from each other? Same with elliptical galaxies and spiral galaxies. Can you tell me how they're different from each other? If you can't, then you should double check our notes from a couple days ago. If you didn't take very good notes, you can still access my online notes and look at some of that, or you can go to the Google class. I'm sorry, not the Google Classroom, the our online textbook that we have, and I haven't assigned you to look at section 26.2, but certainly you could do that if you needed some more information. Where are we going? Well, your assignment for yesterday said that you were going to be able to listen, describe some evidence for the Big Bang, and we're continuing with that today. So, what's next? I need to just try to switch my screen here. I wanted to look at yesterday's assignment that you had, and you were supposed to do some questions from this website that talked about the Big Bang. And our first question was list and describe 4 pieces of evidence for the Big Bang. And you weren't supposed to copy and paste. You were supposed to read things and then try to restate it in your words. So, from the site, it very clearly goes through 4 things. So, the first one says the redshift of galaxies. Now, if that's all you said was redshift of galaxies, you didn't explain it enough. Okay? So, here's the thing when the galaxies are redshifted, what we know that means is that those galaxies are moving away from us. Now, if all galaxies in every direction are moving away from us, then think about it. At some point in the past, they must have been closer together. Oh, if they were closer together, well, how close were they? If you go far enough in the past, was everything back smushed into one clump? Okay, so if everything's moving apart, it must have been closer together in the past. Try to explain it as best you can in your words. The microwave radiation, that's our second point. So the idea here, they said during the Big Bang, the universe was incredibly hot. Okay. Now, right now, if we look out at the universe, uh, if you have the idea, like many scientists did, even 50 years ago, 70, 80 years ago, 100 years ago, if you have the idea that the universe has always been here, will always be here, it's always been the same, then in that universe we have some really hot spots, stars, and even entire galaxies. But we've got these vast spaces in between where there's nothing, and that space in between the galaxies should have no energy. It should just be zero for energy. The Big Bang says that no, the entire universe would have been really hot at some point in time, and we should be able to see that. So when the microwave background radiation was discovered in 1964, that was a huge step in giving evidence for the Big Bang. The people that were working with this idea of the Big Bang had suggested that we should be able to see some leftover radiation. So it was predicted, and when a predicted result shows up and is supported, that lends a lot of power to the theory that predicted it. Okay, the next one, the mixture in elements. All right, so some of you aren't so fond about the math work, but there are people who model our understanding of physics and the universe in mathematics. And those people working on the Big Bang actually model mathematically model what this Big Bang should have done and what the universe would have looked like. And that model tells us what sort of elements we should see and how they were created, when they were created, and how much there should be in our universe. And when we look out at the universe, it matches. That's evidence. This fourth point that's listed here says, and again, it goes back to the idea that people thought for a long time that the universe was static. It didn't change. They thought it's always been here, it'll always be here, it's never going to be different. So, what that does for us, if we look at a galaxy that's relatively close to us, and then we look at galaxies that are very, very far away, we know that the light's been traveling for a long period of time from those galaxies. And when we look at the galaxies further away from us, essentially we're looking back further in time. Those galaxies look different than the ones that we look at that are younger today. Older galaxies look different. So it suggests to us that there is change that happens in our universe. Now, when I look at these points, I think some of them are easier for a beginning student to understand than others. Okay? And the one that I think all of you should really, focus in on is this redshift of galaxies. And I'm going to try to show you something else in just a bit to help with that. The microwave background radiation, you maybe don't entirely understand what that's about. However, I'm going to tell you that is something that, excuse me, that is something that really kind of brought many, many scientists on board with the Big Bang Theory because it was predicted and it held up, and it's been tested. So I think those are maybe the two that you could focus on for a beginning student. Let's see, what other questions do we have? One was, when did the first hydrogen atoms occur? And so now I got to look into this tab on history of the Big Bang. And it says basically at about a second after the Big Bang, the universe had cooled down enough that some elements like hydrogen could exist. And it says in some form. So just like in stars, Excuse me. I got a little tickle in my throat and I'm trying to make it through this. We know that in stars, the matter occurs as a plasma, so it's not neutral atoms. And the simplest atoms would be hydrogen, which is one proton, one electron. Um, so when I read this and it says that after about a second it's cooled far enough that we can have hydrogen in some form, I'm thinking that the protons have kind of stabilized, and so we have these primitive little hydrogen atoms. Now, the next question was how long did before we got some neutral atoms? That says about 380,000 years after the Big Bang, things had cooled down enough that you could actually start getting some neutral atoms. And I think we had one more question, and I gave you this was a multiple choice with only two answers. It says in the Big Bang, the universe expanded into space, or in the Big Bang, the space of the universe expanded. Which statement seems the most accurate? It's a little bit of an interpretation question because it doesn't in this article state that outright. If you read a little bit about Big Bang, though, and we look at some other sources, what they all tend to say is the Big Bang was not, there wasn't space here already, and we have an explosion that occurs into our space. The Big Bang is actually space itself expanding. And so the second answer, in the Big Bang, the space of the universe expanded. That's the one that fits the description of the Big Bang better. All right. So next, I have a video clip here. It's a slow motion watermelon explosion at 3,200 frames per second. And with my Smart Notebook software, what I could do is take a marker and I could identify one of these pieces of the watermelon. I'm just going to outline it in red. I guess I'm not just outlining it, I kind of colored it in a little bit. I'm going to take another piece of the watermelon and color that one with blue. I'll take another piece of watermelon and color this one green. I'm going to play my video just a little bit and stop again. All right, and I'm going to repeat. So here's my blue piece. Here's my red piece. Here's my green piece. Play the video just a little bit. And green piece kind of rotated, but I was watching it. It's down in there. Blue piece is kind of up over here. Red piece is right out here. Maybe we can do one more. Red piece is up in here. Blue is up over here. Green is down here. Now, what I want to do with that is if I draw an arrow backwards from the last piece through the first piece, and I draw an arrow backwards from the last piece through the first piece, and if I draw an arrow backwards from the last piece through the first piece, you notice how all of the arrows come together at one central point. So this is exactly what astronomers were looking at. So Edwin Hubble, you're going to read about him in the reading assignment a little bit. He's looking out through the biggest telescope in the world, and he's seeing that these little fuzzy nebula that we could see out there are not, in fact, in our galaxy. They're actually entire other galaxies of stars, far, far, far away from us. And he measures and he sees that they're all moving away from us, essentially all of them. The only galaxies that you find that are moving towards the Milky Way, there's a few of them that are relatively close to us. But if you look at distant galaxies, they're all moving away from us, and that's in every direction. So if we look out this way and it's moving away from us, and we look this way and it's moving away from us, and if we look down here and it's moving away from us, and over here it's moving away, well, it's getting bigger. Well, then just imagine what must have been like in the past. And so if you actually rewind this and go back into the past, that object is coming back together. And we start out with our nice little watermelon. Okay, so what we're seeing is this. Now, all this stuff that you see here, this is space itself. It's actually space that's expanding. The matter isn't expanding, space is expanding. So I wanted you to think about that um, as you go through it. I've got some of my class notes here about Big Bang, but basically, this first one's about that red shift, that if things are moving apart, at some point in the past, they must have been back together. The microwave background radiation was predicted by Big Bang, and so when we find it, that's a big piece of support. The elements in the universe matches what we see. Um, I have one more that wasn't in your other sources yet, but the fact that the sky is actually dark at night. If you think about that one, the universe is thought to be infinite in size, and there's an infinite number of stars. So in every direction, there should be a star. Why does most of the sky look dark to us? And what scientists would tell you is because the stars in that direction haven't had enough time for the light to reach us yet. So there's a limit to the time of the universe. There's a limit to how far back it goes. The universe has only been around for about 13.7 or 13.8 billion years. There hasn't been time for all the light from those stars to get to us. And so, therefore, we see some dark spots. I know that's kind of a hard one to accept and wrap your brain around, but let's focus back on those first two. Microwave background radiation was predicted, and the fact that of all the red shifting of the galaxies tells us that things are spreading apart. All right, so what you need to do, I've got a assignment for you to read from the online textbook, and I want you to answer some questions from that. I am planning on giving you some sort of quiz on Thursday. At this point in time, I honestly don't know what that looks like. Is it going to be the same sort of quiz I've given in the past, or is it going to be something very different? I have a lot of thinking to do on that. Please make sure that you are turning stuff in. At the time that I'm making this video, there's still about, I think 3 or 4 students that haven't done any checking in on Google Classroom yet today, at least not in my class. So please make sure that you are checking in, that you're doing your assignments, and yeah, we should be good. Good luck. Um, I don't think this will take you 86 minutes to do this assignment, so that means you gain a little bit of time in your day. Please use it well. Enjoy. We can't be at school, and for some of you, that's maybe not a good thing, and for some of you, that might be a great thing. But either way, try to make the best of it, and we will all get through this. So stay safe, and hope to see you soon. Bye-bye.